All right, we're back. We're going to be on page 203 this time of note 16. And we're talking about polar, plotting polar. If you didn't watch the previous video, I suggest you watch that first. So what does a negative r mean? You have to do when you're plotting a point. So in my mind, you go, so I'm going to write like a mathy thing. I'm going to say, what am I going to say? Well, I'm going to write a not mathy thing. Walk backwards. So you basically walk along the same line as theta, but instead of walking forward, you walk backwards. So if you were looking in, so if you're looking in, you walk in. This is if r is less than 0. If you look into quadrant 1, you're gonna walk into what is what's catty corner or whatever diagonal, I guess, to quadrant 1 is quadrant 3. So if r is negative and you're looking in quadrant 1, so any angle between 0 and pi over 2, you're going to walk into quadrant 3, which always feels a little weird. Quadrant 2 will put you in quadrant 4. Quadrant 3 will put you back in 1. And then quadrant 4 will put you into quadrant 2. So there's no alternative. Like, these are the only options, which feels a little weird at first. Like, if you have a first quadrant angle, you are definitely either plotting a point in the first quadrant or in the third quadrant, no exceptions. Because you can't break that, and you'll feel like you want to at certain points when we get to graphing, but there's nothing you can do. So walk backwards is my answer to that. Negative theta value, that just means go clockwise. So rotate clockwise. That one's a little more normal. That's what it's meant all year. Every time you have a negative theta, right? Positive thetas are counterclockwise, starting at the positive x-axis or the polar axis if you're talking in polar. And negative will be clockwise from the positive x or the polar axis. So let's see what we can do. We want to convert from polar to rectangular and rectangular to polar, which is a really common thing to do, especially for points. It's not as common to do for curves because polar curves tend not to have very nice rectangular representations, and like vice versa. So if it looks good in rectangular, it tends to look bad in polar. But let's see. So r is the distance from a point in the plane to the pole. So that we know how to do. I'm going to do a little picture for us, but we know that the square root of x squared plus y squared is going to equal r. Or, so sometimes you use this. It's actually, in polar, it's more common for you to think that r squared is x squared plus y squared. That's like a more common way of thinking about it. So theta is the angle measured in center position passed through xy. We've done this a million times. These are just point in the plane problems. And so what I usually do with that is I would say that theta prime, if you're not, you might use theta hat. That's like a really common thing to do. So theta with like a little hat over it. I use theta prime. Later in your life, there's another use for prime, but it's never ambiguous, so it's not a problem. So theta prime is your reference angle. That's going to be the tan inverse of the absolute value of y over x. Really important that you use the absolute value so you don't mess that up. So this is your reference angle. And so the actual angle, you want to fix the quadrant, right? And to fix the quadrant, you use all the formulas, right? So if you're in quadrant 2, it's pi minus the reference angle. Quadrant 3 is pi plus. In quadrant 4, you can either use the negative of the reference angle, which is like more direct, or you can use 2 pi minus. Like, any of those are up to you. I probably should have written those down, but I didn't. So what are you going to do? All right, plot the point in the first quadrant, sketch our usual right triangle, and figure out x and y in terms of r and theta. So this, again, will feel like something that we have done multiple times because we have. So here, let's say that this is xy. So drop this down, that. So this is r, which we know is the square root of x squared plus y squared. Doesn't really matter at this point. This is our theta. Here's y, here's x. So if I want to find, the relationship between x, r, and theta. So I'm going to use this, and then I'm going to use this. And so that looks like I have adjacent and hypotenuse. So I'm going to say that the cosine of theta is x over r. But when you're dealing with polar, the way you really want to think of this is that x is equal to r cosine of theta. So that's how we're going to think about x when we're talking about converting from polar to rectangular. Rectangular to polar, we use our other formulas. You need to figure out r, you need to figure out theta. When you're going from polar to rectangular, you need to figure out x and y. So x is going to be our cosine. And then when we're doing y and r and theta, so here's y and then r. So that's going to be opposite and hypotenuse. So sine of theta is going to be y over r. And you might recognize these a little. So there's a couple of places where you might recognize these. One place, and this is not super surprising, when we talked about polar form of a complex number, we had, so let's see, new color because it's kind of random. We had e to the I theta equals cosine theta plus I sine theta. So if we multiplied through by r, we would get, and then this was, where was I going with this? Polar x equals y equals x equals r, oh, yeah, I got it. Maybe I got it. I don't know. Multiply through by r. R e to the I theta is r cis theta is the notation that we use, right? R cosine theta was the first part of the complex number, and r sine theta was b, the second part. So this was a plus bi in rectangular, but it might as well have been x plus y times I. So in that case, you get r cosine is x and r sine is y. It took me a little while to get there, but I got there. So we've seen this before, and we even called it polar when we saw it. So Euler's formula popping up, and cis form also popping up. So these are your formulas. You have to memorize these. You're going to use them all the time. So r squared is x squared plus y squared. Tan of theta is y over x is like the safest, easiest way to remember it. But remember, there's like a lot of nuances there, what quadrant you're in and all that stuff. Absolute values matter. X equals r cosine, y equals r sine. Should be vaguely familiar because we did that when we talked about polar form of a complex number. Also, when we talked about point in a plane problems, right? We said that cosine was x divided by, we called it r at the time because we were thinking of a circle. And it's the same idea. All right, let's try to do these. Use the formulas and some common trig sense to convert these points. So this is a rectangular point. The first one, I'm going to look at immediately and say this is on the unit circle. And so I actually already know that r is 1. And because it's on the unit circle, like what point on the unit circle corresponds to 1/2 radical 3 over 2? That's pi over 3. So when you write it, remember it's r comma theta. So it's going to be 1 comma pi over 3. All right, let's say you didn't know any of that or you didn't remember that. You can actually calculate r. So this is the work, but I wouldn't really show work on this, but it would have been the square root of 1/2 squared plus radical 3 over 2 squared, which is the square root of 1 over 4 plus 3 over 4, so 4 over 4, which is just 1. This, we would have said that theta is the tan inverse. I mean, it's first quadrant, so we don't really need absolute values here. Radical 3 over 2 over 1/2, so just radical 3. But then you have to remember that the inverse tangent of radical 3 is pi over 3. So either way, you're going to have to know that at some point. All right, what can we do here? So I'm going to tell you the way that I would do this. I would do this as, do you remember vectors? You remember unit vectors? So with vectors, we had that the vector v was equal to the magnitude of v, and then the unit vector, which was cosine theta sine theta. Oh, cram it in there. Hold on. Let me move this a little bit. I got this. Don't worry. We're all gonna, oh, we're not gonna be fine. hold on. How do I not do that? I can't not do it. Here we go. There. All right, let me try one more time. We have got this. Oh yeah, there you go. Okay, so we had this sine theta, all that, so I could write sine theta and have it look nice, right? So you can think of polar in very much the same way. So to write a point in polar, we have r, and then it's going to be cosine theta, sine theta. And so I tend to think of it as just 6, and then, so it'll be cosine 7 pi over 6, sine of 7 pi over 6, and then that's unit circle, and so we have that memorized, hopefully. So negative radical 3 over 2, negative 1/2. So the point you end up with, distribute the 6 in there, which is like a weird idea, but if you think it's analogous to vectors, so it feels kind of right. Negative 3 root 3, negative 3. So that's going to be the point. So here we're going to get negative 3 root 3, negative 3, and everything's going to be fine. If you don't like that, you can do, you'll see it's essentially the exact same work. So I'm doing all the work that I wouldn't do in blue. X is going to be 6 cosine 7 pi over 6. So look at that. We're going to find the cosine of 7 pi over 6, and we're going to distribute a 6 to it. Look at that. Same deal. Y is going to be 6 sine of 7 pi over 6. So again, same idea. Don't lose sight of the fact that these are working exactly like vectors were working with their magnitude and direction angles, because it's really a similar process. It's just like you call it something different, and they have slightly different properties and things you can use, but still, we know. All right, how about this one? So how much work do you want to do on this one? The work that I would do is I would look at this point and be like, negative 4, 4 is going to be here. So it's going to cut this quadrant directly in half. I know which angle does that. So I'm going to say theta is 3 pi over 4, because it's cutting the second quadrant directly in half. Then, if I were to drop this, this is 4, this is 4, so I know that r is 4 root 2. So I know the answer, and I would go over here and I would write it. So what's really nice about polar is that it's just an extension of things that we already know, right? We're repackaging them, we're thinking of them slightly different ways, but they're all things that we already know. So if you don't like what we just did, which you probably should, you can do the work. You can say that r is going to be the square root of negative 4 squared plus 4 squared, which is going to be, so that's 2 times 4 squared, right? So it's the square root of 2 times 4 squared. Take the 4 squared out, that's 4 root 2. And then theta prime, right? The reference angle is going to be the inverse tangent of, you do the absolute value. So 4 over 4 is 1. So that's pi over 4. But then you have to think, what quadrant are we in? So we're in quadrant 2. So maybe a different color. Quadrant 2. So that means that theta is pi minus pi over 4, which gives me 3 pi over 4, which I already knew. So I recommend that you do these in the best possible way. You know, it's kind of your call. How can I do the next one in a way that's really similar to the one that I just did, right? So look at that. I had negative 4, 4, and it gave me 3 pi over 4 and 4 root 2. This feels like a really similar problem. And when you're doing things that are really similar, like try to draw patterns and see, find patterns, draw something is a word that I can't think of. Draw inferences. I don't know. Look for patterns. Use patterns. So negative 3 pi over 4 cuts this directly in half. And then I get a hypotenuse of 8 root 2. So 8 root 2 is here. But how does that happen? Well, that's got to mean that this distance is 8, but the coordinate here will be negative 8 because the distance is 8. And then this distance will be the vertical distance. I just realized like you can't see what I'm indicating. This distance is 8, but because it's a directed distance, you get negative 8 for the coordinate. And then this distance is also 8. That's how you get 8 root 2. But the y coordinate will be negative 8. So I think we're going to get negative 8 when we do this. So I'm just going to put that down. So -8, -8, by using 45, 45, 90 triangles, basically. If you don't like that, I think you should, but you could do x is 8 root 2 cosine of -3 pi over 4. So remember, cosine's an even function, so the cosine of -3 pi over 4 is the same as the cosine of 3 pi over 4, which is going to be -root 2 over 2. So it's 8, or, so -root 2 over 2. Sometimes it is convenient to think of it as -1 over root 2. In this case, it's very convenient to think that because you get 8 root 2 and -1 over root 2, which is just -8. And then y is going to be 8 root 2, the sine of -3 pi over 4. So in the third quadrant, sine and cosine are both negative. So and 3 pi over 4 is the same thing as sine and so all the pi over 4s, their sines and cosines are absolute values are the same. I'm struggling. So this is just going to give me -8 again, basically, is what I'm saying. So we did the work and we got the same results. What I'm going to do is zoom out so that you can just like take a look at everything. And I'm going to stop this video here, come back, and we will keep working on these. So I will see you in the next video.